the ground electrode conductor is removed from the ground rods and terminated in the main disconnect, and the two ground rods are also terminated there, the installation could be considered code compliant, specifically referencing section 250.62c3, which does permit the ground electrode conductor to be connected to the ground bar. In this specific case, the ground bar is connected to the main disconnect, and that main disconnect is connected to the ground rods. This creates a continuous grounding path from the grounding electrode system to all the branch circuits. However, there is a potential concern that could arise with this configuration. It involves the ground electrode conductor and the equipment grounding conductor from the service feeder being in parallel. This parallel configuration means that if the equipment grounding conductor fails, the ground electrode conductor will then carry the fault current. This action could potentially overload the ground electrode conductor, causing it to fail, resulting in a loss of grounding for the branch circuits. To address this concern and mitigate the risk of the ground electrode conductor overloading, the electrician should install a bonding jumper between the neutral block and the ground bar. The purpose of this bonding jumper is to ensure that a continuous grounding path always exists, even if the equipment grounding conductor happens to fail. Additionally, it is vital that the electrician ensures that the neutral and ground are isolated at the panels. Proper isolation will prevent any neutral to ground faults from occurring within the panels, which could pose a safety hazard. Overall, the installation could be considered code compliant if the following modifications are implemented. Firstly, remove the ground electrode conductor from the ground rods and then terminate it in the main disconnect. Secondly, terminate the two ground rods also in the main disconnect. Thirdly, install a bonding jumper between the neutral block and the ground bar. Fourthly, make absolutely certain that the neutral and ground are isolated at the panels. Elaborating on each of these points to provide a comprehensive understanding. Firstly, the ground electrode conductor's termination point is critical for proper grounding. By moving it from the ground rods directly to the main disconnect, you're ensuring that the grounding electrode system is directly connected to the service equipment. This direct connection provides a low impedance path for fault current, which is essential for effective overcurrent protection. Secondly, terminating the two ground rods at the main disconnect reinforces the grounding electrode system. Ground rods provide a path to earth for fault current, and by connecting them directly to the main disconnect, you're maximizing their effectiveness. The number and placement of ground rods are important considerations which should be based on local codes and soil conditions. Thirdly, the installation of a bonding jumper between the neutral block and the ground bar is a crucial safety measure. This jumper provides an alternative path for fault current in the event that the equipment grounding conductor fails. It ensures that a continuous grounding path is maintained, which minimizes the risk of electrical shock. The size of the bonding jumper should be appropriate for the size of the service conductors, as specified in the National Electrical Code. Fourthly, maintaining the isolation of the neutral and ground at the panels is essential for preventing unwanted current flow. When the neutral and ground are bonded together at the panels, it can create a parallel path for neutral current, which can lead to nuisance tripping of circuit breakers and other problems. By keeping the neutral and ground separate, you're ensuring that current flows only on the intended paths. Section 250.62c3 of the National Electrical Code (NEC) specifically addresses the connection of the grounding electrode conductor. This section allows the grounding electrode conductor to be connected to the ground bus within the service equipment. The intent is to provide a direct and effective grounding path. The ground bus must be securely connected to the enclosure and be of sufficient size to handle any potential fault current. The connection must also be readily accessible for inspection and maintenance. In the configuration being discussed, the parallel paths of the ground electrode conductor and equipment grounding conductor can present concerns. While the NEC allows for multiple grounding paths, it's important to understand the potential implications. When these conductors run in parallel, a portion of the fault current will flow through each path based on their respective impedances. If one of these paths has a significantly higher impedance, it can force a disproportionate amount of current through the other path. This can potentially overload the lower impedance path, especially if it is not sized to handle the full fault current. To mitigate this risk, it's essential to ensure that both grounding paths are properly sized and installed. The equipment grounding conductor must be sized according to NEC Table 250.122, based on the size of the overcurrent protective device protecting the circuit. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. The bonding jumper between the neutral block and ground bar is another critical element in ensuring a safe and effective grounding system. This jumper provides a low impedance path for fault current to return to the source in the event of a ground fault. Without this jumper, the fault current would have to travel through other, potentially higher impedance paths, which could increase the risk of electrical shock. The bonding jumper must be sized according to NEC Table 250.102 cone, based on the size of the service entrance conductors. It's also important to ensure that the bonding jumper is securely connected to both the neutral block and the ground bar, using appropriate connectors. The isolation of neutral and ground conductors at the subpoles is another important aspect of a properly installed grounding system. This separation helps to prevent the flow of neutral current on the equipment grounding conductors. When neutral current flows on the equipment grounding conductors, it can create voltage drops and electromagnetic interference, which can negatively impact the performance of sensitive electronic equipment. The NEC requires that the neutral and ground conductors be kept separate in all subpanels, with the exception of the service entrance panel. This is typically achieved by using separate terminal blocks for the neutral and ground conductors and by ensuring that there are no unintentional connections between the two. When installing ground rods, it's important to follow the requirements outlined in NEC Section 250.53. This section specifies the minimum length and diameter of ground rods, as well as the spacing between them. Ground rods must be at least 8 feet long and have a minimum diameter of 5/8 inch, unless they are made of stainless steel or other approved material. The spacing between ground rods must be at least 6 feet, and they must be driven into the ground at an angle of no more than 45 degrees from vertical. The depth at which the ground rods are driven is also important. The top of the ground rod must be below permanent moisture level. This helps to ensure that the ground rod makes good contact with the earth, regardless of weather conditions. The connection between the grounding electrode conductor and the ground rod must be made using an approved connector. The connector must be listed for direct burial and be suitable for the type of conductor being used. The connection must also be protected from corrosion, using a suitable sealant or tape. The water pipe electrode is another common element in a grounding electrode system. When used as a grounding electrode, the water pipe must meet certain requirements outlined in NEC Section 250.52a on. The water pipe must be metallic and be in direct contact with the earth for at least 10 feet. The connection to the water pipe must be made within 5 feet of the point where the water pipe enters the building. The connection must be made using an approved connector and must be protected from corrosion. It's also important to bond around any insulated couplings or sections of plastic pipe in the water pipe system. This ensures that the water pipe remains electrically continuous, even if there are non-conductive sections in the system. In addition to the water pipe and ground rods, other types of grounding electrodes can also be used, such as concrete encased electrodes and ground rings. Concrete encased electrodes, also known as UFO grounds, are typically used in new construction. They consist of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. Ground rings consist of a bare copper conductor that is buried in the earth in a continuous loop around the building. The loop must be at least 20 feet long and be buried at a depth of at least 2.5 feet. When designing and installing a grounding electrode system, it's important to consider the specific conditions at the site. Soil conditions, local codes, and the type of electrical equipment being used can all affect the design of the system. It's also important to consult with a qualified electrician or electrical engineer to ensure that the system meets all applicable requirements. Proper grounding is essential for electrical safety. A properly designed and installed grounding system can help to protect people and equipment from electrical shock and fire hazards. It's therefore important to take the time to understand the principles of grounding and to follow all applicable codes and standards. The ground electrode conductor, often referred to as the GEC, plays a critical role in the grounding system. Its primary function is to connect the service equipment to the grounding electrode, such as ground rods or a metallic water pipe. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. It's crucial to use the correct size GEC to ensure that it can safely carry any fault current back to the source. The material of the GEC is also important. Typically, it's made of copper or aluminum. Copper is generally preferred due to its lower resistance and better corrosion resistance. However, aluminum can be used if it's properly sized and protected from corrosion. The installation of the GEC must comply with NEC Article 250. It must be securely connected to both the service equipment and the grounding electrode. The connections must be made using approved connectors and fittings. The GEC must also be protected from physical damage. If it's exposed to mechanical stress or abrasion, it should be installed in conduit or otherwise protected. In addition to the GEC, the equipment grounding conductor, or EC, is another important component of the grounding system. The EGC provides a path for fault current to return to the source from electrical equipment and appliances. It's typically a wire that runs along with the circuit conductors in a raceway or cable. The size of the EGC is determined by the size of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. It's crucial to use the correct size EGC to ensure that it can safely carry any fault current back to the source. The EGC must be connected to the metal enclosure of the equipment or appliance and to the grounding terminal in the electrical panel. The connections must be made using approved connectors and fittings. The EGC must also be continuous and unbroken throughout the circuit. Any splices or terminations must be made in a junction box or other enclosure. The bonding jumper is another essential element of the grounding system. It's used to connect non-current carrying metal parts of the electrical system together to form a continuous grounding path. This includes metal conduits, metal enclosures, and metal equipment frames. The size of the bonding jumper is determined by the size of the circuit conductors, as specified in NEC Table 250.102. It's crucial to use the correct size bonding jumper to ensure that it can safely carry any fault current back to the source. The bonding jumper must be securely connected to the metal parts using approved connectors and fittings. The connections must be made in a way that ensures good electrical contact. The neutral conductor is the conductor that carries the unbalanced current back to the source in a 3-wire or 4-wire system. It's typically identified by its white or grey color. The neutral conductor is connected to the neutral terminal in the electrical panel. In a properly wired system, the neutral conductor should only carry current that is unbalanced between the phase conductors. If the neutral conductor is carrying excessive current, it could be a sign of a wiring problem or an overloaded circuit. The ground fault circuit interrupter, or GFCI, is a safety device that is designed to protect people from electrical shock. It works by monitoring the current flowing in the circuit and comparing it to the current returning. If there is a difference of more than a few milliamps, the GFCI will trip the circuit, cutting off the power. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. They are an effective way to prevent electrical shock in areas where there is a risk of moisture or contact with grounded surfaces. The arc fault circuit interrupter, or SI, is another safety device that is designed to protect against electrical fires. It works by detecting arc faults, which are small electrical sparks that can occur in damaged or worn wiring. If an arc fault is detected, the SI will trip the circuit, cutting off the power. SIs are required in many new homes and are an effective way to prevent electrical fires caused by faulty wiring. Electrical inspections are an important part of ensuring electrical safety. They are typically conducted by a qualified electrical inspector who will check the electrical system for compliance with applicable codes and standards. Electrical inspections can help to identify potential hazards and ensure that the electrical system is properly installed and maintained. Regular electrical inspections are recommended to help prevent electrical problems and ensure the safety of people and property. Electrical safety is a serious matter, and it's important to take steps to protect yourself and others from electrical hazards. Always follow safe work practices when working with electricity, and never attempt to repair or install electrical equipment unless you are qualified to do so. If you have any questions or concerns about electrical safety, consult with a qualified electrician. By following these guidelines, you can help to prevent electrical accidents and ensure a safe electrical environment. Always to energize circuits before working on them. Use appropriate personal protective equipment such as gloves and safety glasses. Never work on electrical equipment in wet or damp conditions. Be aware of your surroundings and avoid contact with energized pots. Follow all applicable codes and standards. If you are not qualified to work on electrical equipment, call a qualified electrician. Remember, electricity is a powerful force that can be dangerous if not handled properly. By taking the necessary precautions, you can protect yourself and others from electrical hazards.